Hi everybody and welcome. Had to bring a new square root picture in because look, it's a root and it's square. So it's going to be our final video in this series of this week's square root videos. It's kind of bringing us to the conclusion of this review skill. So we're going to be feeling comfortable with all of our square root type operations after our video today. So our goal after watching this, we'll be able to actually multiply radicals or multiply square roots here. So our vocab word for today is multiplying radicals. And this just tells us that the radicands, or the numbers on the inside, multiply if and only if the index, or the power, of the root of each radical matches. So for example, you can take the root of 2, multiply it by the root of 8, and get the root of 16. That's okay. They're both the square root. But if we had something like the root of 2 times the cube root of 8, those have a different index, or is a root to a different power. So that doesn't work. Can't do anything with that. Can't simplify it any further. We just have to leave the answer just like we found it. Nothing more that can be done there. But again, we can use this property here to help us with some multiplying. So where does this come in? Well, it comes into multiplying these radicals, but also into division. So why this is important is when we're looking at dividing radicals, there is a rule with these. We are not allowed to have a radical in the denominator. So we need to have these rationalized. So we don't want to have a irrational number like the root of 2 on the bottom. We can have those on the top, but not on the bottom. So how do we get rid of things like these? Well, our goal here is to rationalize this, and again, using that skill of multiplication. So we're going to try a little trick. Whatever's on the bottom, if it's a radical, we just multiply by that. We have to multiply by 1. We can't change the quantity or the balance. So root 2 over root 2, if we divide those, just equals 1. So we're not changing this in any way. We're just rationalizing the bottom. So on top, we have 1 times the root of 2, or just the root of 2. And on the bottom, we have the root of 2 times 2, or the root of 4. Well, you'll notice the root of 4 is just plus or minus 2. So whatever is inside on the bottom, our radicand, if we multiply by that, that's just what comes out as our answer. So for example, on our next one here, if we multiply the root of 28, you can know before you even do this without having to do that multiplication. On top, you'll have 12 times the root of 28, and on the bottom, you'll have plus or minus just 28. We can simplify this further because 12 divided by 28, we can, again, both even numbers, divide them both by 2. And actually, we can divide them both by 4, so we can get even more simplified than that. So we'll get 3 times the root of 28 over 7. So again, further and further and further simplifying these, it's our goal to multiply by whatever root is on the bottom in order to get rid of the root, and we're happy when we have a whole number on the bottom. This gets a little bit more difficult when we are looking at further rationalization questions. So our denominator here that we're trying to rationalize isn't just a power. We can't just multiply this by the root of 5 because we'd still have some square roots on the bottom because it's not just root of 5, it's 3 minus 5. So there's something called the conjugate. So if you had 3 minus the root of 5, what can we multiply that would get rid of all of those radicals? Well, there's actually only one thing. You take those same numbers and you change whatever sign is in the middle. And if you do this, you can set up your binomial box that we're actually going to need for this here. What we're going to see, 3 times the root of 5, 3 times the negative root of 5, we'll get 9. We'll get minus 5 here. Because, again, if we multiply both of those, we get the root of 25. And we simplify that out, it just gets us 5. Here, we would get 3 times the root of 5. Here we would get negative 3 times the root of 5. So our diagonal is 3 minus 3, or just 0. So we end up with 9 minus 5, or just 4, as our answer there. And we've rationalized our denominator. So we need to do that to both the top and the bottom in order for this to work. So 3 plus the root of 5, 3 plus the root of 5. So we'll have 2 times 3 plus the root of 5. And then on the bottom, we'll have 9 minus 5 Or if we simplify this further, it's 6 plus 2 times the root of 5 all over just 4. So whatever you have on the bottom, basically you're keeping those same numbers. So 6 in the root of 2, 6 in the root of 2, we're just adding in a plus sign. And again, when we do that, we'll be able to have a simplified answer. So a little bit of box method multiplication for our bottom terms to see what our actual ending denominator is. And actually on the top, we're going to have to do the box method as well. So if you're like, Mr. R, this box method multiplication with these radicals is a little bit confusing, well, let's actually go over a few additional examples of box method multiplication with some radicals. So first, sometimes we are able to just distribute. And in this case, we have cubed roots, so that makes it, we can do that, right? We're allowed to multiply because the indexes are the same. So we'll have the cube root of 8 here, plus we're going to have the cube root of 24. Now, we always want to be checking these to make sure that there's nothing that we can factor out. So again, if we think about this one, we could have the cube root of 4 times the cube root of 2. Actually, no, I made a mistake there. That's a cube root. That's not a square root. We actually already know the cube root of 8. So the cube root of 8 here, I'm just double checking, is positive 2. So that's just 2. And then secondly, we can actually, this is the one that we can factor out. So we can have the cube root of 8 times the cube root of 3. Can't do anything with the cube root of 3, but we just did this one right here, right? So we'll have 2 plus 2 times the cube root of 3. So a little bit of simplifying after we do that, because we are, again, factoring, and always want to simplify these radicals wherever we're able to. And again, we do that by breaking them out into their individual factored pieces. All right, so now let's get back to what we were talking about before, Mr. R. What happens when I need to multiply these binomials when there's radicals? Well, we set up the sides of the boxes just like we did before. So 2, 3 times the root of 7, 4, and just the root of 7 here. And we multiply the edges just like we normally would. So 4 times 2 gets us 8. 4 times 3 times the root of 7 just gets us 12 times the root of 7. Here, 2 times the root of 7 actually just gets us 2 times the root of 7. And then our last one here, 3 times the root of 7 multiplied by the root of 7 will get us 3 times 7, because, again, square root of 7 times the square root of 7 is just 7, or 21. So we can put all of these things together. Conveniently, our diagonals are like terms in this case. So we have 8 plus 2 times the root of 7 plus 12 times the root of 7 plus 21. So adding up all 4 of our boxes one at a time. Combine some like terms. 8 and 21 get us 29. And again, some more like terms. 2 times the root of 7 plus 12 times the root of 7. Again, we can add these together. It gets us 14 times the root of 7. So that would be our final answer for that multiplication problem. Because 7, can't break it down into any more simple factors. It just is what it is there. 7 times 1 are our only options. So I would say a bit of a more challenging video, a bit of a more challenging skill. Like always, though, with these challenge videos, bring those questions to class, bring them to small group time, ask them via email if you